In this podcast, we'll be building on our ideas from Snell's law, and we'll be looking at the phenomena of prisms. We'll be looking at total internal reflection, and we'll be calculating critical angles. Let's start by looking at prisms. In a prism, the index of refraction changes for different wavelengths of light. On the left-hand side, we've got our incident white light, and white light is a combination of many wavelengths. And what I've done here is I've drawn my normal to the boundary, like we did in the last podcast. So that's perpendicular to the boundary, and I've labeled my incident angle. Then on the other side, I've labeled my refracted angle. And what we can see is that violet light bends more. And what this means is that violet light slows down more than red light, which means that the index of refraction for violet light is different than the index of refraction for red light. And in fact, that index of refraction for violet light is greater than the index of refraction for red. And we can see that effect. We can see that violet light bends more than red light. So the indices of refraction can actually vary for different wavelengths. Let's take a look at an example. It says a beam of white light is incident on a triangular glass prism with an index of refraction of about 1.5 for visible light, producing a spectrum. This is exactly the situation we were just looking at. Initially, the prism is in a glass aquarium filled with air as shown above. If the aquarium is filled with water with an index of refraction of 1.3, which of the following is true? Okay, so in this scenario, we start out with air, so n is equal to 1. But then what we're going to do is we're going to change that n value to be equal to water of 1.33. The index of refraction for the prism remains constant at 1.5. So let's take a look at our options here. Option A is that no spectrum is produced. Option B is a spectrum is produced, but the deviation of the beam is opposite to that in air. Option C is the positions of red and violet are reversed in the spectrum. Option D is the spectrum produced has a greater separation between red and violet than that produced in air. And E is the spectrum produced has less separation between red and violet than that produced in air. So let's take a look at these options. No spectrum is produced. That's not true. You will still get a spectrum. You'll still get bending of the light rays. B, a spectrum is produced, but the deviation is opposite to that in air. An opposite deviation means that the light would bend away from the boundary instead of toward the boundary. But in both cases, if you look at our n values, the n for the prism is greater than the n for air, and n for the prism is also greater than n for water, which means that in both cases, the light is actually going to speed up when it's out here, and it's going to slow down inside of the prism. So we're going to get the same effect, which means C is not the answer either. In order to have a greater separation, we would need to have a bigger difference between our indices of refraction. But what's happening here is we're going to a smaller difference between our indices of refraction. So the correct answer here is E. The spectrum produced has less separation between red and violet than that produced in air. Let's take a look at another phenomenon. This phenomenon is called total internal reflection. I'd like you to consider what happens if I have a light source. And I'm sending a beam of light at the boundary between two media, and in this case, the light is speeding up when it exits the medium, and it's bending. Now, since it's bending away, I can tell that N1 is greater than N2. In other words, this medium is something like glass, and this medium is something like air. And what happens as I change this incident angle, I still get light bending, but what happens here? What happens here is this is the point where the refracted angle is 90 degrees. And we call that the critical angle. Past that angle, what happens is we get something called total internal reflection. In other words, the light beam bounces inside, and what you will see is that this angle and this angle are equal. Or if you choose to measure it from the normal, this angle and this angle are equal. So we can compute the critical angle, and again, the critical angle is the point at which this refracted ray will lie right along the boundary. So let's do an example of that. It says, if the angle of incidence is 45 degrees and the angle of refraction is 33 degrees, sketch the situation. Okay, so I'm going to draw two substances, and it says the angle of incidence is 45 degrees. That's 45 degrees, and the angle of refraction is 33 degrees. And there's my sketch. Now, I'm going to go ahead and assume that out here I've got air, and then here my index of refraction is unknown, and my substance is unknown also. Maybe it's glass, maybe it's water, maybe it's plastic, maybe it's something else. Part B asks me to find the index of refraction for the substance. I can do this with Snell's law. I can say 1 times the sine of 45 degrees equals n times the sine of 33. This is a job for my calculator. Once again, make sure we're in degrees. Okay, 1 times the sine of 45 divided by the sine of 33. And my n value is 1.298, or approximately 1.3. Now I'm going to find the critical angle for the substance. Now to find the critical angle for the substance, I'm going to turn the light beam around, and I'm going to ask this question. First of all, here's my substance, where n equals 1.3. Here's air, where n equals 1. What I'm looking for is the critical angle, and that is the angle at which, it's the incident angle at which it produces a refracted light ray that has an angle of 90 degrees. So again, it looks just like this picture up here, where the light ray is coming in at an angle such that the refracted light ray lies right along the boundary. Now this is just a Snell's law problem. I can say that 1.3 times the sine of my critical angle equals 1 times the sine of 90. And I can use my calculator to solve that. So 1 times the sine of 90 is just 1. I divide that by 1.3, take the inverse sine, and I get 50.28 degrees. So I just determined that this angle is 50.28 degrees. What does this critical angle mean? If I am past the critical angle, in other words, if I'm over here in this yellow region, I will get total internal reflection. Just like this diagram, the light ray will bounce around inside the substance. If my angle is less than that, then I will get refraction. So in the green region, I'll get refraction, or bending of the light ray.